All right, as our final topic in correlation and kind of looking at two variables, we're going to look at what's called a linear regression. Now, in general, a linear regression is going to help us to actually estimate the actual value of future or past performance based on a set of data. Okay? So just review it a little bit. Remember that in correlations, we have two variables. We typically call the x variable the explanatory variable, and then y the response variable. So we're trying to see how y changes as x changes, and that's the whole idea of correlation. Now the graph we look for, remember we call it the scatter plot, where we have the different dots for the x's and the y's, where generally x is the explanatory and y is the response. And we'd look for patterns and things like that. So once we have that scatter plot, we get the correlation. Now remember, in the scatter plot, we're looking for the form, so generally linear or nonlinear, the direction, so positive or negative, and then the strength of this relationship. And we would measure that with that R value, R being that correlation somewhere between -1 and 1. And then obviously, if you have outliers, like a lot of statistics, will really throw off your results. So if you have something that's out of the pattern, that will significantly reduce your correlation. So here's just a quick example. It says, which of the following statements about the correlation are true? So a correlation of 0.2 means that 20% of the points are highly correlation. That makes no sense. Perfect correlation, that is, when the points lie exactly on a straight line, results of R of 0. Well, that's not true. It would be an R of 1. Correlation is not affected by which variables x and which is y. That is actually true. That is actually true. It does not matter which is which. Correlation is not affected by extreme values. We just said that's not true because outliers will change it quite a bit. And then we just said that correlation of 0.75, that the relationship is 3 times as much as one that's 0.25. Not necessarily true. It's just a number between -1 and 1. So our goal is to actually take these correlations and actually make a mechanism that will actually help us predict future values. Okay? So we do that with what's called a least squares regression line. This is sometimes also referred to as the line of best fit. We'll also abbreviate this a lot with LSRL, least squares regression line. So a linear regression or a least squares regression allows you to find a line that best fits our data. Okay? So if I have a scatter plot with a bunch of points, this one looks somewhat positive, I'm going to try to find the line that would best match that data. Which line would best approximate that relationship? And this is going to be called the least squares regression line. So a least squares regression line we generally will write as y hat equals ax plus b. Now the y hat, as we call it, that is our predicted y value. That's what we think it will be. If you have some value of the explanatory value, so if you have some value of x, you can find a predicted value for y. And it's just a line. It's just a regular old line. So in this we call a is the slope. So if you remember mx plus b, this works kind of like m. And then b is the same variable. It's just the y-intercept. Okay? So you could also write this in other ways. I've actually seen other calculators write it. I've actually seen them write it as y equals bx plus a, which is kind of bizarre. But the big thing is the slope of the line is always in front of x, and that's just true from algebra. And then the number with no x is going to be our y-intercept. So that's going to continue to be true, just like any line equation that you've ever seen. So the idea of a least squares regression line, essentially what we do is this is just kind of a graphical example of how this works. Now we will do our line. Most of our calculate of our least squares regression line will be done on Desmos. But essentially if I have these scatter plot points, I want to try to find their vertical distance to some unknown line And so these are my distance. These are typically what we'll call the squared distances. So if you think of all these distances, we'll call them all D, D1, D2, D3. In a least squares regression line, what you're trying to do is you're trying to make, if you add up all these distances, you want those to be the smallest as possible. So we're trying to figure out what's the smallest sum of all these distances I can make. And that's how we'll calculate our A and our B, get our slope and our y-intercept. Now once we find this slope and this y-intercept, slope and intercept will work just like it always has. So what I want to go ahead and I want to do is I want to go ahead and kind of review what slope and y-intercept are. So slope is going to be when you have some kind of amount that increases or decreases when x increases by 1. So it's how much is the y going up as x goes up by 1. So if I have some regression line, y equals 2x plus 5, that means the slope is going to be 2 over 1. So every time y goes up 2, then the x will go up 1. And if it's a negative slope, it just means that the y is going down a certain amount as x goes up by 1. So that's slope, rise over run, however you remember it is fine. Now, if we do the intercept essentially is what happens when x is 0. Or it's the starting point. So it's kind of the start when x equals 0. If x equals 0 makes sense. So sometimes it wouldn't, like if I'm saying how much money would you make if you work no hours? Well, no hours makes sense, but other parts of regression, an x equals 0 might not make sense. But graphically, it's obviously where it's going to cross the y-axis, why we call it a y-intercept. So this is b, and then our slope, how much you go up and over, is our a. So my goal is to do an example, and I'm going to show you how to do this on Desmos. So we'll see if we can find our regression line based on Desmos. So if you look at this, this is my data. So I have 40, 60, 70, 73, 75, all these pairs for x and y. Now x is the average for each student. So each of these values of x, so x is the score on some kind of evaluation. So this is the evaluation they gave their teacher. And then below y, this is their grade in the class. So we want to know basically if you have a higher grade or if you have a higher evaluation, do you typically have a higher grade? Or if you have a lower grade, do you have a less favorable evaluation of that instructor? So we have all these things. So what I'm going to do is I am going to put this in Desmos, and I'm going to figure out how to do that. Okay, we're going to look at how we do our linear regressions on Desmos here by using this recording. So what I would do is I have this data for evaluation and grade. So what I'm going to do is I'm going to first create a table. So I'm going to hit this plus button, and then I'm going to go down to where it says table. Now the x's I said for us are our evaluation scores. So 40, 60, 70, 73, 75, 68, 65, 85, 98, and 90. And then my y's were the actual course grade, so what you were getting in that course. So 40, or 10, 50, 60, 65, 75, 73, 78, 80, 90, and 95. Okay? So if I go to my screen here, I can make my scatter plot with these values. Okay? So let's go ahead and make you can see some of our points here if I scroll out. So there's kind of my points that I just put in, right? So my goal is to find the line that will best fit these points, okay? So it's a pretty easy process. You have to make sure it looks like this. What we will do is I have to type a very specific thing in. So you notice that up here this says x1 and y1. That's very important. So what I'll do for my regression is I'll type a y, and then I'm going to do what's called an underscore. Now, an underscore is the shift and the underscore button, which is right next to 0. You probably all know where that is. So I do y1, and then I'm going to right arrow. You see how it says equals 10 elements in the list? Because that means there's 10 y's in our list. Then I'm going to put my tilde, which is the approximation symbol. It's the top left corner of your keyboard. So we're saying y is related to a. A is our slope. And then I have x. Now my x's are x1, so I'll put a x1, and then I'll put plus b. So if you notice, what it did is it gave me a line, it's made this red line, and it told me a and b. A and b are the slope and the y-intercept of my line. So this line is y equals 1.34 x, because a is the slope, so it's in front of x, plus, well, I guess it's minus because it's negative, negative 29.31. So if you do the regression, it actually shows you, but I want to at least show you how, what we're actually finding. So this is my regression line. This is where I found this. So now that we kind of know this, we'll jump back over and we'll try to figure out how we can actually find these, use this line to do some things with our regression. Okay, so now we have our regression line. We have y equals 1.34x minus 29.31. And the way we defined it, we said x was the evaluation score and y was the grade in the class. Okay, so however you define it is fine, it doesn't matter, you could switch those, but this is the way we did it. So this says, use your equation to predict what evaluation score for a student who scored 81. So basically, what is x when y equals 81? Well, all we'll have to do is, in this case, we'll plug in 81 for y, because y is our grade. Now, a lot of times you'll just plug in for x, so this is almost probably more difficult than a lot of the problems we'll encounter, but pretty straightforward. You just do 81 equals 1.34x minus 29.31. So it'll be 81 plus 29.31, which is 110.31 equals 1.34x, and then we'll divide both sides by 1.34. So that's going to give me an evaluation score of 82.32 as my estimated score. So if you looked at the correlation, obviously the correlation was very strong. It was 0.9. So it's a very, very good chance that if you got a good grade, you were going to give a good evaluation and vice versa. So the slope in this case is 1.34. So that's going to basically mean every time that my grade goes up, if my grade will go up 1.34 points every time my evaluation score goes up by 1 point. Because the slope is 1.34 or 1.34 over 1. So every time the grade goes up, the grade's going to go up 1.34 every time the evaluation score goes up 1. Now we know that doesn't always happen that way. If you feel better about your teacher, doesn't mean your grade's going to go up. But in this problem, that's what it looks like. So do you think these are related? I would probably say yes, obviously, because the R is very high. If you looked on Desmos when I calculated it, R was 0.9042, and I would almost say that is not unlikely, because if you have a better rapport, you like your teacher better, more likely you'll do better in the course. Okay. Now, the one thing I would mention, just remember when you're using regressions, when we're doing these predictions, they don't always work out. Sometimes you have a problem that's called extrapolation. Now, extrapolation just means that's basically when you're using a regression line to predict something that's way outside the timeline, right? So if I do something with, like, say, I don't know, a price of food or price of gas or price of something, right? Well, if I have a bunch of information, say from 1950 to 2000, and I have a bunch of information, that's fine, and I make my regression line. Well, I don't want to use this to predict what the food price will be in the year 3000. So we really think this trend is going to continue like this forever? Now, it could, but more likely the trend might change. So we have to be somewhat careful when we're doing these, because this extrapolation could show that it doesn't always show the value in the proper range. So we'll work on more of this next week. We'll do some regressions and use them in some different situations.